is classification. What classifiers do is they also are boxes that taken an input, the machines that given an input produce an output. They make a certain estimation of something. Like, for example, we took the example of cows and ducks. Is it a cow or is it a duck? So in other words, the output belongs to a category, a class in a category. So in other words, it is cow, duck, let us say horse, and so forth. You have to tell what it is. Now, machines work with numbers. It's all mathematics. So the way they do it is they will produce for you a certain, not the labels, but they will produce the probability of a cow, probability of a duck, probability of a horse. And what you would do is you would pick the biggest of the lot, right? So if it seems that it is, let's say, a 40% probability it's a cow, or 50% probability it's a cow, and 25% probability it's a duck, and 25% probability it's a horse, you would go with cow. Right? You do you find the maximum value. That's sort of getting into the details. Now, classifiers are interesting. They're interesting in quite fundamental ways. These days, a lot of these machine learning models, large language models, for example, that you engage with, they are instruct GPT models, namely the ones that you can talk to, ask questions, and they respond with answers. They are actually classifier models. They are considered next token predictors. So suppose you give a sentence, the cow jumped over and you give it to the box, and the box emits the word moon as the next word, as a completion probably, or you ask it a question and it begins to answer. What it is really doing is it has a finite vocabulary. So you again have a category. The category is the vocabulary itself, is the vocabulary. And let's say that the word starts with artwork and they go all the way to the word zephyr. And all it means is the word moon happened to have the highest probability. This machine thought that the most appropriate word to emit is moon. And then it can continue on. You feed moon back to the input and you ask, what next? And it might say the next best word to predict is literally a punctuation, full stop. Right? And so forth. So these next or more formally, next token prediction LLMs are next token prediction engines, and thus are classifiers. Now, there is a debate in the research community, are they really next token prediction engines? There's emerging evidence that actually these large language models are capable of internal construction of thought. They think full thoughts, and then they start generating tokens. So a lot more is going on than we understand. LLMs are one of those mysterious things. We never get quite the feeling that we understand them. In fact, we have very, very, very hazy understanding of what is happening in an LLM. Right? How is it thinking? We don't know. But anyway, we'll keep that aside and focus back on classifiers. See, classifier is essentially predicting that it's a cow is the same as identifying an object to be a cow. Classifiers, if you look at the theory of human knowledge, many civilizations have, in one form or the other, said the same thing, namely that our recognition of the external world, what we call knowledge, is to a large extent our ability to classify. For example, this has been there in the Western philosophical traditions. It's also been there in the Eastern philosophical traditions. For example, the Sankhya philosophy, very categorically, Kapila says that. So, for example, if you encounter an animal that has never been seen, a thought experiment is, would you even recognize it? Or what would your eyes make of it? Or if it is made up of attributes, none of which you recognize, we recognize things by their color, shape, and so forth. But what if there was a being whose attributes were not color, shape, etc., whose properties were not this? Would your sense organs even recognize them? It's a question worth asking. So, so this classification or classifier are fundamental entities that go to the very heart of the question: what is knowledge? Most of knowledge is classification in some sort. And machines think in a very similar way. They take certain attributes of the input. For example, it may say this cow or this animal has 4 legs, that it has horns, that it is big, right? And it has a certain color. Therefore, internal mental model tells us that we should call it a cow. It's a process of recognition. No matter what, each cow is different from every other cow. And nevertheless, and each person is different from every other person. Nevertheless, when we look at each other, we are fairly sure that we are all part of the human species. Right? So that ability is implicit, the mind's ability to classify. Whatever we look at, we are classifying implicitly in our brains all the time. And the same is what the machines are doing. So classifiers actually are a very interesting thing, which says given an X, which is made up of certain attributes, let us say size, color, etc. I took the example of stones. So for example, if I were to show you this stone, it has a certain size, it has a certain weight, it has a certain color. If I were to tell you that it is, tell me what material is it? Is it graphite? Right? Is it something else? A whole variety of things. Granite is the next one I was going to think, but think of something else. Any one of the stone varieties, right? Topaz or whatever. Yes, topaz. Topaz is, well, not quite, but yes. Any one of those things it could be. What you're doing is you are classifying. Right? If you're given a problem, here's the transaction, credit card transaction. You have to decide whether to approve the transaction. And you notice that this transaction is coming from a country that your user has never before visited or seems to have done a transaction from, right? And there's a transaction amount which is for and the object being purchased is some electronics. Right? And so by looking at the attributes of the transaction, which includes the attributes of the user behavior, if you come to the conclusion that this is atypical, this is anomalous, right? It's a classification. It's a fraud detection, or at least an anomaly detection. You're saying there's something anomalous about this transaction. So maybe you will put the transaction on hold and ask the user to call you back. Right? That happens all the time. Right? When you look at objects in astronomy, there's a lot of data that the telescopes gather. If you are asked, are we looking at that little thing that little patch in the sky? Is it noise, or is it the very faint signal of a very, very distant galaxy? That's classification. In fact, AI is heavily used nowadays in astronomy to discover huge amounts of astronomical objects, especially with the James Webb Telescope in the sky. So classification is something that is everywhere, and a lot of problems that we encounter are actually can be formulated as a classification problem. Now, when we talked about regression, I didn't specifically go into any algorithm, but in classification, I'll go a little bit deeper into machine learning and give you a sense of 1 or 2 algorithms today, right? The specific algorithms that achieves. But before I do that, let's say that there is some algorithm. How would you know that your classifier is, how would you train the classifier, and how would you know how well it performs? And the two are interrelated. They are interrelated. Why? Because remember, learning is a reduction of errors. So we need to somehow quantify the errors, isn't it? So let's take to the problem of cows and ducks. Suppose you have a machine, you give it an input of attributes of an animal and you ask it, what is it? And this will produce a probability. Now we'll refine it a little bit. What the machine will produce is a probability of a cow. So if the probability of a cow is more than 50%, let's say if this is greater than 50%, then it is a cow, else it is a duck. Let's agree on something. So this number 50% is called a threshold. So now we will first, so there's a one more step we brought in. We said machine learning algorithms produce, many of them, not all of them, but many of them, they just produce a probability of it being something. Right? And from that, you can come to what it is by applying a threshold. It's a two-step process. Now, 50% sort of makes sense in some situations, but there are situations where it doesn't make sense. So I'll give you an example. Suppose you have a machine that is looking at X-ray images. And as you gradually approach, I suppose it's true at any age, it's a chest X-ray. Right? One of the, by the way, one of the classic data sets that we use, and we will today explore, is called the Wisconsin Diagnostic Breast Cancer Data Set. So, but I'll actually take a slightly different formulation of it. Let's say that you are given an X-ray, and you have to determine, based on the attributes, whether the person does or does not have any indications of breast cancer, right? You have to determine. The original Wisconsin dataset was made up of cellular. It was used fine needle aspiration. We'll talk about that later. But visually, just to frame it in your mind, imagine you're looking at an X-ray, and you stare at the X-ray, and the question is, does this person have any hint of a tumor, benign or otherwise? Right? Any lumps or anything. And as you know, this is of great consequence, because the problem with malignant tumors are they're rapidly dividing cells. And rapidly dividing cells grow exponentially, which means that if you don't catch it early, the cost, the human cost in suffering is exponentially rises. It leads to very invasive procedures, chemotherapies, radiation, and other modalities, right? And even the risk of mortality. So you want to catch it as early as possible. So you're looking at a machine, and imagine that you have a machine and it's predicting the probability of, let me just say, cancer. Or let me just say tumor, any tumor, benign or malignant. And I ask you, given this, at what probability, let's say that if you indicate there is something odd, the patient will be sent for further screening, further diagnostic test, right? More invasive diagnostic test, perhaps a fine needle aspiration, perhaps something as a biopsy or something like that would be sent for. What would be a good cutoff to have? Would you still say 50%? What would you say?
50% is just a coin toss. Right? So we need to go much higher.
Yes.
90 to 95% plus.
Why is that?
So there are two aspects of this. We don't want to miss the false diagnosis as well.
No, it's a screening test. If it come out positive, then there'll be subsequent tests done.
Sure. Okay. Yeah. So maybe take two stages of it. So for the first one, it has to be definitely greater than 50%.
Are you sure greater than 50%?
Because
your reasoning is correct,
sure.
but you're moving in the wrong direction.
Okay.
So we sort of have false negative, but we can have false positive. So probably I would put that much lower, even if it's like 5%. I don't want to take chance of it, the patient's in.
Oh, excellent answer. So see, the basic thing is, I'll formulate it this way. If there is a 50% chance that you will get killed, would you cross the road? you'll be hit by a vehicle, would you cross the road? 50% is too risky. Would you cross the road even at 25% or 10%? You wouldn't, because it's risky. It is exactly the same danger when you leave a tumor undiagnosed. Right? So what you want to do is, even in the least hint of tumor, right? So long as they are not flooding everybody declaring everybody to be having a tumor, you have to pick a threshold, but your threshold has to be very low. Let's say 5 or 10%. At a low threshold, you will mark it. What will happen is that there'll be a lot of false positives. A lot of people who are perfectly healthy, they will be declared needing further test. Right? Now, a lot of people obviously don't quite understand that need in medical parlance. Needing further test means literally needing further test. But some people get quite worried and they start writing their will and things like that. So that's the worst that can happen. But then 1 week later, you do further test and it turns out that the person is perfectly fine. So the damage is acceptable. On the other hand, if there is a false negative, the consequences are terrible because the cancer will rapidly proliferate.
Well,
So you want to put a cutoff low.
It's not that simple, of course, because sometimes additional tests have risks as well. And typically you might be testing 100,000 people. There's a classic medical ethics dilemma, right? Is if you test 100,000 people and 5 of them are positive, but because you're so inaccurate, you get 50,000 people needing further tests, people will object.
Oh, yes, certainly. Certainly. Tom, you do make a very good point. And it also goes to the ethics of the whole thing, as you pointed out, and the fact that devices and things are used to be at least fairly noisy diagnostic tools. And you do bring about a good part of the history of these things. Recently, though, actually these tests have become extraordinarily good in the sense that their diagnostic precision accuracy is very, very good. This has happened only in the last 2-3 years. Google, for example, has chest X-ray interpretation or tool to do classification of anomalies or presence of tumor or something like that. That actually exceeds in its diagnostic ability, exceeds most radiologists. In fact, almost all. It is at par with the best radiologists. And that is a fairly recent achievement. And keeping those nuances and sort of, as you say, oversimplifying it, nevertheless, if you had to pick a cutoff, right, assuming that your equipment is reasonably good, you would take a fairly low cutoff. You would say, let's do. But you wouldn't take a cutoff so low that, 50,000 people are in, like just about any person who comes, you say, well, you need further test, because that becomes an ethical question. Are you making money or are you, and of course the human cost, because all tests that happen after that are a little bit more invasive. They are not just X-rays. So good points. There are certain things where, on the other hand, you want to be absolutely sure. For example, when the Higgs boson was discovered in the particle accelerator, in the big accelerator, people had to be sure that the chance that they have not seen a Higgs boson, that it is just accidental data, right, was 1 in gazillion, right? They had to be absolutely sure. So what is the point at which they say, positively we have seen a Higgs boson, the God particle in the particle accelerator? It is extremely high, 0.9999999 something. And at that value, you say, well, now we might have seen a Higgs boson. And that's the story of Higgs boson. I mean, as a physicist, I find that very interesting, that it was actually discovered before it was declared. It was already observed 2-3 years before, but because people were not absolutely sure, they felt, well, let's keep doing more experiments. So that brings home the point that where you put the cutoff is a question of judgment and very problem specific. And sometimes, as Tom mentioned, it might be a problem also of ethics. So that is that. Now let's build on to that. So cutoff, the reason I brought the threshold question up is I want to finish it off. And I'll just assume that we will work with probabilities, and thereafter the rest, the cutoff part is a decision that people have to make. So let's take a data. I will take a data that looks like this. Just imagine that I have, and guys, by the way, I'll contrive data and call them fruits or something like that. And of course, if you know fruits, you will say, "Oh, wait a minute, fruits don't show this distribution of characteristics at all." Right? But the purpose here is to just explain a topic. So let's take some fruit. We will take blueberries. And let's take strawberries. These days, lots of strawberries are available. I just came from Costco, and they seem to be loaded in strawberries. Now, you would agree that if your x-axis is size, y-axis is weight, most of the blueberries would be somewhere here, small, sized. And now I'm going to, while they will actually show more or less a normal distribution, I will now start stretching the reality a little bit to bring home a point. Imagine that they're like that. And what about strawberries? They're a little bit bigger and heavier. So let's have strawberries like this. And maybe there is some type, well, I don't know if there's any blueberry that can be confused with a strawberry, but we'll pretend they are. Some genetically grown blueberries that are giant. Right? So common intuition says that strawberries are likely to be big and heavy. Something like that. And I ask you, I give you an arbitrary point. Let's take an arbitrary point. That deserves a new color. Let's this. I give you a fruit whose weight is this. Let me call it A, which is tiny and lightweight. Just looking at the picture, what would you say it is? Is it a blueberry or a strawberry? And how confident would you feel that it's a blueberry? Pretty confident, isn't it? On the other hand, if I take a point that is B, now what would you say? What do you think it is? It's big and heavy. It's strawberry, right? And would you be confident or rather shaky about it? Confident. And now, if I were to take a point here, let's take here, C. What would you call C? Yeah, now it's getting a little bit doubtful because it's sort of near the weight of a strawberry and the weight of a blueberry, right? So what happens is, as you go in this direction, your confidence that it's a blueberry diminishes. Your confidence that it might be a strawberry begins to rise up, isn't it? What about you go to point D? Once again, it is in the twilight zone between blueberries and strawberries. Who knows, right? Let me, for illustration, sneak in a blueberry here. It could be a blueberry or a strawberry. But by the time you reach B, you realize that journey from A to B is a journey of increasing probability of a strawberry, isn't it? Given the data, X is the data, namely the weight and the size. So the word given is that confidence comes from what? By observing the input. Right? So whenever you say that, the mathematical notation for that is given. This vertical line is called given, or condition, more formally conditioned on. Right? People who do probability love the word conditioned on, but we'll call it given. Given the input, given the weight and the size, this you are trying to tell what is the probability of a strawberry. And certainly, as you go from A to B, your probability keeps increasing monotonically, isn't it? So then there must be a point at which it could go either way. 50-50, right? It could be, well, strawberry, or it could be a blueberry. So that point, there must be a line of demarcation through the data, such that if you're on this side, it's like the Berlin Wall. If you're on this side, you're in West Germany. If you're on this side, you're in East Germany. Right? There has to be a wall there. So let's draw such a wall. Well, the Berlin Wall is gone, thankfully, but in mathematics, I should have taken a better example. Okay, let's take the Pacific coast, our California coastline. There is a point, very roughly, which demarcates water versus coast, isn't it? So that is a boundary. Let's draw it out. Would you say that this line is a pretty good job of it? Does that make sense, guys? It does make sense. Now, and what I'm going to do today, and not because this algorithm is the only classifier algorithm, but today I wanted to go a little bit deeper. Just as yesterday I went a little bit deeper than the first class, today I'll go a little bit more into the mechanics of building a model. And trust me, it is very simple. I'll try to build it up using first principles. So you realize that your confidence that it is a blueberry or this is proportional to how far you are from the distance you are in the let's call this direction positive and this direction negative, right? So suppose you are at distance d, right, for any given point x being that point, this is the data space. Given any weight and any size, you have a point, you have this point. This point is at a certain distance from this boundary. You realize that your confidence that it is a strawberry increases with distance, positive distance, right? And if you go in the opposite direction, decreases with distance, with negative distance, isn't it? Is that obvious, guys? Right? If this is the negative direction, the more I move down, the more I move south west towards closer to the origin, the more confident I am that it is, the less confident I am that it's a strawberry. More confident I am that it's a blueberry, the converse of it. So I'll just use the word confidence about strawberries. Right? Now, it turns out that common people, they often don't use the word probability. It sounds rather scary. Then what do people do? But almost everybody goes to games, isn't it? And people talk of the odds, or they do elections. Election season isn't more than how many months ago? 6 months ago, right? And if you were listening to the news in this country, and obviously everybody knows that in US, I know that there are people here from different countries, but we had elections in November. So at that time, in every democracy, people are working out the odds of this party winning or that party winning. Do you remember? And you say odds are 10 to 1 and so forth. So what is the definition of odds? It turns out that the definition of odd is probability of something happening. Let's say probability of strawberry as a ratio to probability of it not being a strawberry, namely blueberry. This is called odds. Does that make sense, guys? This is literally the definition of odds, right? And this is the same as, I will just write it P instead of continuously writing the whole word. You would agree that probability of blueberry is 1 minus the probability of strawberry, isn't that? For example, if the probability of strawberry is 80%, the probability that it's a blueberry has to be 20%. Right? So 1 minus P. 1 minus. Now, if you look at this quantity, it's a very interesting quantity that tends to recur in machine learning. But this quantity, for a variety of reasons, is a little bit more manageable and becomes this when you talk not of odds, but log of odds. Log odds. It's just more well behaved. Right? Why? Because if you look at this number, it has the danger of blowing up to infinity. Because if p in the denominator is 1, what will happen to the odds?
Finite.
It will become infinite, right? So you don't want that. So generally, log odds is a little bit more manageable. So when you do log odds, it would be the log of this. And in many ways, what we think intuitively as, our belief, our confidence that it is something, agrees more closely with log odds. Just take it as a sort of fact. Well, it is also true. By the way, guys, for those of you who are mathematicians, you would immediately say, I know you're up to some mischief. Right? It's not a very rigorous argument, and that is true. But I'm leading us somewhere. Right? So just go with it. Is the intuition. Log odds. So you would agree that if I look at the picture, log odds must be proportional to the distance. The bigger the distance, the bigger is my confidence that it's a strawberry. Would you agree, guys? You would agree. And so you would say, well, what is the simplest direct relationship we can do to log odds? You can say, well, why not just make it an equality? Is the distance from the decision boundary? By the way, and this line has a fancy name. It is called, and in machine learning, this term you'll encounter all the time. It is called a decision boundary. What, can we guess why it is called a decision boundary? It literally helps you decide which way would you want to call it, a blueberry or a strawberry. It's called decision boundary. In 2 dimensions, it's a line. Well, in this case, it's a line, but it could be a curve, for example. Right? We will look at other examples where it would be a curve. And in higher dimensions, decision boundaries are surfaces. Right? For example, inside an egg, whether you're in the white part or the yellow part of the egg, the decision boundary is pretty obvious, isn't it? It's the surface of the yellow part. Right? And that's what we are talking about. Right? It's a boundary. It's the boundary of the yolk. Now, what we just did, this derivation that we did, actually, believe it or not, we have derived one of the equations that people find when they come to machine learning rather hard to understand. The way it is, for unfortunate reasons, I've never understood why, it is introduced to people in textbooks using a very scary equation, P, probability, and by the way, it's not P of X, it's really probability of strawberry given X is equal to e to the 1, it is given as this equation, 1 plus e to the minus d of x. Right? It's usually represented in a more complicated way. It is represented typically as an equation, which is written as 1 plus e to the minus, right? The theta dot x plus theta naught. Something like that, some scary equation that you have seen. Has anybody seen this equation and recognizes this? This is the equation, the so-called logistic equation. Logistic equation. But I find it easier. And now I claim that this is exactly the same as this, and I'll just show it to you. So this part, guys, are you all easy? What I said was nothing, I hope, beyond basic high school. Isn't it? And so what we are going to do is take that equation and manufacture this very, very scary equation out of it. Let's do that as a derivation. So it is a log business going on. Now, what does the log do? If you take the anti-log of it, 1 minus p, taking the entire log would make it e to the power dx. So far, so good, guys. This is still high school. I exponentiate both the sides. So exponentiation of the log of something, exponential and log cancel out on the left-hand side, and on the right-hand side, you have a dx. Now what? From this, it is very obvious. Suppose I add on both sides. So this is the same as e to the 1. Now, in algebra, it is legitimate, if you have an equation like this, to take the denominator or to take the numerator and add it to the denominator. But you have to just do it on both sides. So if I take this equation, 1 minus p, and I also bring this in and add it here, p, I'll have to do the same thing on this side. 1 plus this, I have to bring it here. I'll have to do dx. Make sense, guys? And so this and this cancel out. And so what you're left with is probability is equal to e to the d of x, 1 plus e to the d of x. And now if I divide both numerator and denominator by d of x, and this by d of x, you begin to look at something that is very close to the equation. It begins to all make sense. E to the, so this becomes now the logistic equation, e to the minus d of x. Isn't that true, guys?
Okay, maybe I've just been out of school too long, but I don't think you can do the add something to the numerator. I don't think that's valid. Am I wrong?
To the denominator, you can. In fact, in the old British books, it used to be called componendo and dividendo. You don't want to do that. See, here's the thing. If you don't know the tricks, just work out the equation. Go ahead and do it. Yeah. That particular technique in algebra has an old name because I learned the old British way. It used to be called, look at a book that was famous long ago called Holland Knight's Advanced Algebra. And it had a very interesting name. It's more than 100-year-old book. This technique was called componendo and dividendo. Right. So anyway, I'll leave that. But you can see, you don't have to go with me. You can just expand it out and do the long derivation, but you can do that. So there we go. And then you will end up with an equation like this. Now, the only difference is, what is dx? This is, of course, the famous sigmoid equation. And I'll explain its importance. What is dx? This dx, I won't go into derivation because it's a little bit of geometry. Take it on faith that the distance from the decision boundary is, suppose I call this variable x1 and this variable x2, right? The distance is given by theta naught plus theta 1 x1 plus theta 2 x2, right? It can be written as an equation like this. Okay? Now, that takes a little bit of geometric tricks to do that, and I won't go into the derivation. And the moment you realize that that is the distance from a decision boundary, you immediately see the famous equation with which most books on machine learning start, which is that they say that the probability that it's a strawberry, given the input, is 1 plus e to the minus theta naught plus theta 1, x1 plus theta 2, x2, in this particular example. Right? So let's go through it a little bit more and see if it all made sense or not. Oh, by the way, this question about whether it's true or not, we can verify very simply. Actually, I think somebody asked this question. Let me bring some confidence that I'm not just pulling up some arcane text which may not be true in the 21st century. Let's take a number, 1 over 2, and let's take 3 over 6. Right? So suppose I add this to the denominator, 2 plus 1 and 3 plus 6. What does it become? 1 over 3 is equal to 3 over 9. Is that still true? Yeah. Right? And thus the proof. Right?
I stand corrected.
No, it's one of those tricks. I don't know why in the pursuit of so-called modern methods of teaching, all of these techniques are becoming lost art. Today, everybody does, I don't know, differently, the long form. But it is still an art to be able to look at the equation and remember all this bag of tricks that gives you a shortcut. So therefore, let's review what we just did. We just derived the famous and the most widely used classification algorithm. The name of this algorithm is and paradoxically, even though it is and this is what history does actually to things and makes it hard for people who come new to it to get a handle on it. Logistic regression. Logistic regression. Now you say, wait a minute, this is not a regression. We are using it for classification, isn't it? Nevertheless, it's an irony of history that the most popular, the simplest, and the most widely used classifier in the world is called a logistic regression. So some people tend to use the full form, logistic regression classifier, just to be sure that they emphasize the word. But for historic reasons, the word logistic regression has stayed. And actually, there is a justification for it. There is such a theory as generalized regression. And generalized regression says that whenever you can write, like in this particular case, look at this equation. This equation is log p1 minus p is equal to theta. Distance by now we know theta naught plus theta 1 x1 plus theta 2 x2. You remember, you are familiar that this is the equation of a line, in this case, equation of a plane or equation of a line. Right? This is the equation of a line generally, or a linear object in line equation. You say, well, how is it a line equation? You can think of a line equation mx plus b. Now, just bring it all on one side. You can say y minus mx minus b is equal to 0, right? And now you convert y to x2, this to x1, because those were our x1, x2 coordinates in machine learning. And now this begins to look familiar, but just take it as a fact that equation of a line. So whenever you have a function that is equal to a linear combination of parameters, theta 1, x1 plus theta 2, x2, whatever number of parameters there are, any equation that you can write like that, well, not any equation, that is an exaggeration, but say a certain class of equations that can be written like that, a class of functions. These are often called link functions. And so in the language of that theory, which you would say that the log odds is the link to the equation of a line, and therefore logistic function relates to regression, right? So there is a way of thinking of it as a regression. So that's a historic reason for it. We won't go into it. But what have we achieved? Let's step back and appreciate what is it that we have achieved. We have pulled off. Let's go down. We have pulled off a few concepts. We realized that all points, all data are points in a Euclidean space. And this is one thing I must say, guys, that people approach machine learning in different ways. And because people's brains are wired differently. To some, it is just some Python libraries. To some, it is equations. To me, and I hope to many of you, for me, it is geometry, it is visual. To me, every concept in machine learning can be translated into some dead obvious geometry. Okay? Which is why today I took a geometric approach to explain to you logistic regression, which is very simple. If you have blueberries and strawberries, you would agree that there is a decision boundary, a straight line decision boundary in this situation. And the distance from the decision boundary is a measure of how confident you are that it's a strawberry. So far, we are making obvious statements, isn't it? And the next thing that I said is that one measure of confidence is log odds. Right? If you use log odds and thus equate log odds to the distance, what we have done is we have rediscovered the celebrated logistic regression from first principles, just from simple arguments. Is that fun, guys? I don't know. Now, one of the questions that I would ask is, I would like to take you further in this. This field of machine learning, it is in the twilight zone of many fields. It's very interdisciplinary. There's beautiful mathematics, beautiful geometry, topology. There's lots of coding. There's lots of hardware optimizations, infrastructure, operating system theory, everything, all that is pretty much engineering and science and mathematics. There's excellent physics. Everything is converging into this field of artificial intelligence. It's just amazing. And recently there has even been a discovery. I mean, as you know, quantum computers are coming, which will be the absolutely amazing hybridization of physics, math, and computing. That is all on the horizon, especially in artificial intelligence. AI, that's what makes this field so very, very fascinating. But the beautiful thing is the mathematics that you need to understand AI, usually, if you pay a little bit of attention, you realize that you already know it. You have learned it in high school or first year of college. At some point you have learned it. It's not that hard. So now I'll change, we can go into other algorithms, but for today, because we need to do some practical things, just like yesterday, how do we know that our classifier is doing a good job? So what happens is, suppose ground truth is it's supposed to be a cow. Something is a cow. And let's say that we had 100 cows, and you ask how many predictions said it was a cow, how many predictions said it was a duck. So if the machine predicts cows to, looks at a cow and says cow, did it get a right answer? It did get a right answer, right? Or we can stick to strawberries and blueberries, it doesn't matter. So let's take cow as the positive case. Just by convention, we have to pick one, we'll call it the positive case. And in the case of a tumor, it's very obvious. Is it a positive finding? In medical, any problem is a positive finding. So you want to come away, your report saying it's all negative, right? So when a cow is predicted as a positive, this is a positive. Let's say pick a number between 1 and 100. How many cows are positively identified? Let's say about 70 of them. Out of 100 cows, and let's say that you have ducks, and you have 100 ducks. So given a duck, and if 70 cows were identified as cows, it means that 30 cows are misidentified, isn't it? Likewise, if your machine predicts, so let's say that, let's pick a number, random number. I'll just say, let's say 60. 60 ducks, the machine predicted correctly to be ducks. But what happened to the rest 40 ducks? Cow. The machine somehow mistook it to be a cow, right? So if cow is the positive case, then these become false positives, isn't it? These are true positives compared to the ground truth, you know that. True positive. And these are true negative. You know, they are genuinely ducks, isn't it? True negative. What about this guy? They were cows. You misidentified them as ducks. They are false negatives. False negatives. So that's the vocabulary. And what would this make? This whole thing, what is it called? It's called, it's a lovely name. And very like when you get the name, you'll both smile and see that it's very apt. It's called the machine's confusion matrix. Isn't that name lovely? And the good thing is, if you have a confusion matrix, think about it this way. If you have a confusion matrix that look like this, 100, 100, 0, 0. What would you call this model? It's a perfect model, right? It has made no mistakes. There are no false negatives. There are no false positives. This is what you want to do is train your machine to come closer and closer to this. It will never reach this most of the time. Data is too complex, too noisy. Your machine will be useful, but not perfect in real life.
If this were to be the case, isn't it a case of overfitting the model?
Not necessarily. Sometimes data comes that clean. For example, I'll give you an example. If I were to give you the mass of a cow and the volume of a cow, of an animal, you would realize that in the data space, ducks would be in reality here, close to these would be the ducks. Like this is the weight and this is the size. And the cows are big and heavy. They will be far off. Now, you would realize that just as with human beings, even for machines, they would have a very easy time telling a cow apart from a duck. They wouldn't easily confuse this, right? And so the fact that you have a perfect confusion matrix, a perfectly accurate model, means one of two things. The problem was very easy, right? It didn't have noise. The separation, what the right technical word is, the separation. So here's the technical word you use. In the feature space, namely this space, features are the weight and size. In the feature space, the classes are well separated. Would you say this? Would you say this phrase here? In the feature space, the classes, what are the classes? Cows and ducks are well separated. It has to be, because if there is an overlap, there is no way in this. Think about it this way. Where is this picture gone? Yeah, let's look at this picture. You realize that there is no machine, however intelligent, that can possibly create a perfect confusion matrix here. There are genuine levels of overlap, isn't it? The only way you could do that is, as you mentioned, is if you built a model, contrived model, which went like, let's take a color. Suppose you make a decision boundary, which is like this, like this. What about this model? This would get it perfect. But what you say, just intuition tells you that now this is really pushing it, isn't it? Why? But now translate your intuition. Something tells you that this is not a good model. Would you agree? Right? It almost looks silly. Now let's translate it into more formal language. What's wrong with this model? That what is wrong is that, remember that when you build model, you have a sample of reality, right? What does it mean? You have made it fit exactly to the sample. When another sample of reality comes, oh boy, this model will start making lots of mistakes, right? So it is overtly complex model. Right? And so there is a progression from simple to complicated models that you can have. Are we together? And this is the famous bias variance trade-off that I will talk about. So guys, just absorb this picture because I have to scroll down. Just absorb this picture for a moment and accept that this is this river that is meandering its way through the landscape is probably not as good a model as we would want, right? So now we will look at two extremes. There is a ground truth. You can make a model that is too simple, or you can make a model that's too complex, right? Let's take an example. Let us say that your data looks like this. You get a data in which you have two things, yellow for oak. That you have data that is like this, right? And outside data that is like this. Now you look at this, what sort of models can you make? Suppose I made a model, I'll take multiple colored models now. I'll take a white model, which is a polynomial of degree 1, namely a line. Poly, right? Which says this is the decision boundary. Anything above it is pink, anything below it is yellow. Would you be impressed with this model of reality? You wouldn't be too impressed. It is too simplistic, too simplistic. Ground truth is a bit more complex, isn't it? If you came with a different model, and if I took another model, this one, model 2, let me call it model 2. The white one was model 1. This was model 1. And let's make a crazy model, because we need one crazy one, that goes like this. It goes, let's go very carefully and, oh, what about this model? Model 3. Model 3 is pretty impressed with itself. It got all the answers right, isn't it? It would have the most perfect confusion matrix. But you would have a sneaky feeling that if you took a different sample of the data, it probably won't hold up. Right? So you say overtly complex. Because looking at it, the ground truth is actually favoring model 2. Right? So what happens is, so another thing is, how do we build models, AI? That is the perennial problem. Because when data comes, you don't know what the ground truth complexity of the data, isn't it? The whole reason you model is you're trying to find out about, build some model, some hypothesis, and therefore you're trying to discover a decision boundary in the classifier, isn't it? Now, because you don't know a priori how complex the ground truth is, you have this problem. You scan from simple to complex, right? Don't start with most complex. The problem that you'll have is you have overfit the data. Notice that overfit the data, isn't it? Whereas the straight line hardly fits the data. So there is such a thing as a bias. It is the famous bias variance trade-off. A bias variance trade-off, right? What it says is, if you plot, suppose you have the ability to complexify a model, right? Complexity is along this axis. One easy way is to think of polynomial regression, like doing it with a polynomial, trying to fit a polynomial to data. So the degree of the polynomial, example, degree of a polynomial, degree of a polynomial. Now, I'll tell you another fact about polynomials. I'll just take a quick digression into polynomials. People, sometimes, you can fit data to a polynomial. It remains very easy to interpret. There's something beautiful about polynomials that you probably haven't noticed. So polynomial is theta naught plus theta 1 x plus theta 2 x squared plus theta 3 x cubed, etc., theta n x to the n. This is a polynomial of degree n. Are we together? Now we'll do something interesting. If you take polynomial, poly, degree, and I don't know if you have ever observed or noticed it, and you see, count the number of bends. Right? So n is equal to 1. What is the equation? It is theta naught plus theta 1 x. That is basically a line. How many bends does a line have? Zero. It doesn't bend. It's line. Right? Well, if it bends, it wouldn't be called a line. Right? Now, let's look at the equation of degree 2. N is 2. Theta naught plus theta 1 x plus theta 2 x squared. An example of it, for example, is parabola. How many bends does a parabola have? It has one bend. Now, what about n is equal to 3, theta naught plus theta 1 x plus theta 2 x squared plus theta 3 x cubed? How many bends can you guess this has? So I'll give you an example. 2, right? Or this is also an example. Many of these, 2 bends. Do you see a trend out here?
N minus 1.
Yes. So degree n minus 1. N minus 1 bends. So that gives you actually one of the loveliest tricks that I use. Sometimes I just stare at the data if it is low dimensional, and I just start looking at the number of bends. If I can hand draw the decision boundary, I will start counting. For example, especially luckily when it's two-dimensional data, I'll just draw it up. And then I'll ask, okay, how many bends do I see? And then right off the bat, I would take a polynomial of 1 more degree and immediately make a model. And then it is an interpretable model, unlike opaque random forest or gradient boosting and many support vector machines and so forth on neural networks. It's a very transparent model, interpretable model. Right? And it's really a delight actually to just step into a room, see this problem, visualization of the data, and immediately be able to write the equation that would form the best model for that data. Right? And so the only job of gradient descent is to find the best parameters, theta naught, theta 1, theta 2, etc., whatever degree I chose. Right? So that is it. But that brings me to this famous bias variance trade-off. Let us say that you make a model and look at the number of errors it makes. When you train a machine, you will observe that if you plot the errors, and as you make the complexity of the model higher, like adding terms to and building different models of different complexity, you see a classic trend. In the beginning, your model will be obviously too simple, right? As in this case, look, the white line is hardly a good representation, isn't it? Then what happens is, so errors will be high, but as you make the model more complex, it will reach a point. And once again, if you make the model too complex, errors will again begin to rise. Is that obvious, guys, from this picture? Yeah. Right? That something like that would happen. And this famous curve is called the bias variance trade-off curve. Isn't it dead obvious that something like this would happen? Why? Because as the model's complexity approaches the ground, and where will it have the minima? Ground truth. Where it is closer, the closer it comes to the ground truth, the better the model will be in complexity, right? And so this reflects closest to ground truth. Like, for example, the khaki or the brown line in this picture, right? In this picture that we have, the brown line intuitively says that the model that is a model that can be the brown line will probably have the least errors. Make sense, guys? So this is the bias variance trade-off. In this thing, people sort of further refine it to say that errors are made up of 3 components. In any machine learning model, the errors are made, total error, is made up of 3 kinds of errors. So people have sort of a breakdown. Right? First of all, the first dichotomy is reducible errors and irreducible errors. So first, let's talk to the irreducible error. And that's the bad news. It says that most data sets and most models will have irreducible errors. So one source of irreducible error is inherent noise in the data. Right? If you have noise in the data, you can't help it. Or if there's too much overlap between the classes, you can't help it. Right? What does it mean? The attributes that you have are not enough. So one source of it is noise. The other is insufficient information, informative inputs, X. Let's make it very concrete. Remember our entrepreneur, she was trying to open an ice cream shack on the beach. And if she built a model, as she did yesterday, using just the temperature, now she will observe that whatever ice cream she estimates based on the temperature is sort of a rough measure. There'll be more or less. Why? Because she did not consider other variables, such as how windy was the day, was it a work day or a holiday? Because when are the beaches populated? When dads and moms are not at work and they bring the kids to the beach. How choppy this water is, dangerous the water is, how windy it is. So there are other factors that determine the population on the beach, isn't it? And So irreducible errors speak to two things: inherent noise in the data and the insufficiently informativeness of the inputs that you have taken is not the whole reality. But the fact that you're looking at a partial reality is reflected in the fact that you have irreducible error in the model. Then there are reducible errors. What are reducible errors? Your model should be not too simplistic or not too complex. When you have a model that is too simplistic, there is and I will not explain that kind of mathematics in this basic course. We do it when we do the more formal courses, but I'll just mention it to you. A too simplistic model errors, this kind of errors are called error kinds. And these are reducible error kinds. Too simplistic, these are called bias errors. Bias errors. By the way, this word bias has nothing to do with social biases, and it has nothing to do with neural networks' weights and biases, right? It is a statistical word, a bias. So the bias is a sort of a homonym. It has many different meanings in different contexts. The other is a too complex model. Too complex model errors. This kind of errors, which are induced when you make, like for example, try too hard to fit the data. That is why it's also called overfitting errors. And I hope the word overfitting is fairly obvious if you stare at this picture and look at the green line, isn't it? Or if you look at this picture and you look at that khaki green line, right? That kind of errors are called variance errors. And these words have statistical meaning, but I won't delve too much into it. Variance errors. So what do we say? Reducible errors are made up of bias errors and variance errors. Bias and variance errors, isn't it? So now when we go bias and variance errors, isn't it? So now when we go back and look at our picture, the initial graph that we made, in which we say complexity of the model is the x-axis and errors is the y-axis. What happens is, suppose this is the total error curve, total errors. You would agree that this is your irreducible error, according to the way that we just understood, isn't it? It's your irreducible error. What about now, if you just break this line into the other causative factors, you will realize that there are two factors. This is, and take my, something like this. This is the bias errors. In other words, if the error that comes from making your model too simple, obviously has to, well, actually it will go down to zero. Why did I asymptote it? I shouldn't have flattened it. So let's say this, right? If your error comes from keeping the model too simple, common sense says that as you complexify your model, those bias errors will disappear, isn't it? Or they'll get mitigated. And the other error that this thing is made up of is the variance errors. Like the variance errors, I am not drawing it too accurately, but this is the variance errors. Why? Because variance errors are the errors of complexity, over complexity, excessive complexity. So obviously, if you take a very simple model, it doesn't have complexity, so you don't have variance errors. And you see that the white line is the summation of these two errors, plus the irreducible error. Does that make sense, guys? Right. So that is the interpretation of all of this. Now, a couple of metrics. I won't tell all this. So there are these lovely metrics. I leave it to you as an assignment to find out what exactly these things mean. Accuracy. Accuracy, I'll explain. Precision, recall, and F1 score. F1 score. There are other metrics. They are called area under ROC curve, but we are almost out of the theory time. I would like to get into the lab. And so there are lots of other measures, but I'll explain what accuracy is. Remember, in a confusion matrix, the diagonal is the good thing, right? True positive and true negative. Do you remember that? Let's go back here in our confusion matrix. Look at this. You would agree that these are the good ones. 70 and 60 are the correct ones. Everything else is the error. So what you do is you do 70 plus 60, the principal diagonal, over the total. Now what's the total? 100 cows and 100 ducks, 200. Right? So you say that this machine got 130 out of 200 right, isn't it? That is 65% accuracy. Though I must leave you with, and I'll let you discover the meaning of the rest of that, because that will be fun for you to explore. But and one incentive to make you explore is to tell you, unfortunately, you can't quite trust accuracy. Why would I make that statement? You can't quite trust accuracy. If somebody says, I have a tool and it is 95% accurate, would you be delighted and be willing to put down $1 million to buy it? No. Can somebody tell me why or guess why? Let's go back to the cancer situation. Let's say there's a tool that checks and tells whether you have cancer, right? All right, or actually, let me take a piece of real history. See, for the longest time, we now retrospectively look back at the medical science and we realize that before the modern medicines came in, the penicillin, the antibiotics, and the modern drugs came in, most of the drugs that were there in the 19th, 18th century were of close to zero efficacy. Sometimes they were, I mean, of course, as a palliative, you can take things, but to cure serious diseases, most of those drugs were of very limited, almost no efficacy. So then if the doctors couldn't cure you, why is it that doctors have existed for thousands of years and they have been very popular? So I have a hypothesis. Right? So imagine that I'm a quack and I claim to be a doctor. I go into a village and I open a shop, hang a shingle. And every time a patient comes, the first thing I tell him, that my dear boy, don't worry, I'll take care of you. Right? You'll be fine. And then I give some medicine that my professor taught me, probably will cure this person, and you give it to that person, and that person gets cured. Right? There is a sequentiality bias here. Remember, I talked to you the previous time. So let us say that I'm not bogus. I actually went to the medieval medical school. So I believe in the medicine that my professor has taught is to be given for this illness. The person goes away, takes the medicine, and gets cured. By today's modern science, we now look back and say that medicine is absolutely nonsense, right? And yet, I was a very popular doctor in medieval times. People said, wow, what a great doctor. You go to him and you'll get cured, right? How do you reconcile these two opposites? Anyone? What are the flaws involved here? You know, in the light of modern medicine, that whatever I was giving was nonsense in a past incarnation. So how do you explain that? Anybody would like to venture a guess? It goes to the heart of what we are talking about in classifiers and what metrics to look for. I'll just venture a guess. See, most diseases are self-limiting. In a general population, the incidence of serious things like cancer is somewhat limited, right? Let's say the chance of cancer is 1 in 1,000. So when I tell everybody, my dear fellow, I'll take care of you and give some medicine and the person goes back, human body is also self-healing to a large extent. Most illnesses are, infections that body runs its course, right? Or upset tummy and so on and so forth. Mostly infections. They run their course and you're okay after some time. So flu, things like that. So considering that the body heals itself, most people are going to get cured. What will be my success rate? It will be close to 100%, 99.9% success rate, isn't it? And yet, I'm doing nothing. Right? So accuracy of what was my prediction? As a doctor, I'm predicting that you'll be fine. When I'm saying, my dear fellow, you'll be fine, I'm making a prediction, you'll be fine. Right? My predictions are 99.9% accurate. And yet, it's a very ineffective treatment because the genuine person who has a problem, I would miss that case. Right? So that is the problem with accuracy. There is another flaw, by the way. In the first session, we talked about the flaw of sequentiality. See, a patient comes, is feeling upset tummy, gets a medicine, goes home, gets cured. Therefore, that person attributes the cure to the medicine, invariably, not to the fact that the body is self-healing. Right? And that sort of explains why, despite the fact that in the light of modern medicine, we know, or much of the medieval medicines were nonsense, those medicines still had a strong following. There was a time, if you go back and look at the history, even in US and in Europe, people had the so-called patented mixtures that they would sell from town to town. My special mixture that will cure you of this disease and that disease and tonics and whatnot. Right? So that is the sequentiality bias we talked about in the very first session. And also, this is a cautionary tale in looking at accuracy as the sole measure of a model. Right? What was the problem here? There was a fundamental class imbalance. Right? There is a class imbalance. The ratio of people who don't have cancer or something very serious to the number of people who do have something serious, the ratio is overwhelmingly in favor of essentially healthy people with minor illnesses. When you have a class imbalance, accuracy, you have to use it with caution. So let us say that there is a 90 to 10 ratio. You know that a baseline model would be accurate 90% of the time. Right? So you need a model whose accuracy exceeds 90%, isn't it? So you have to look at accuracy with caution. You have to know how to look at it by looking at the class imbalance first. Right? And that is where other measures like precision, recall, etc., also are informative. But I leave that as an exercise for you, and I'll end the theory part today. So are there any questions before we take a 5-minute break, and then we'll go into the labs? So welcome back. Now we'll do the lab session. So as I do the lab session, I thought this thing that I told you, by the way, this fact about polynomials, it has a name. It is called the fundamental theorem of algebra. Right? And what are bends cause roots to happen in equations, right? The zeros to happen. But so I related a very simple thing in geometry. So suppose we have a data that looks like this, guys, that looks like this. How many bends does it have? 2. And so what would be a good polynomial degree to model this? 3rd degree polynomial. If you try to do a polynomial of degree 1, you'll end up with a model that will look very unsatisfying, right? Would you agree that this line is not a good model of the data? Right? It follows a general characteristic, but it's not as good a model. It has no bends. So what happens if you go and do a model of degree 3? Much better, isn't it? Right? That's the point I'm making. And this is the point I'm making, that if you ever see data and you can count the bends, your first temptation should be to just model it to the polynomial. You will get it right. Now, I want to talk about the bias variance trade-off. So you look at this data now, and when you do look at this data, what can you see? Would you say you see how many bends? 2 bends. What happens if you model it? You make an overtly complex model. Right? Suppose you try to model it with, I think I took a polynomial of a very high degree. Oh, degree 11, 11 degree polynomial. It's a really flexible model. What can you tell about this model? You see that it's sort of overfit the data, isn't it? It's trying too hard to get through the data. And one of the problems that you see with very flexible is that what is happening at the tail ends, the two tail ends, left and right. Do you see those floppy tails that I was talking about, those wagging tails that I was talking about of a dog? This is unnecessary bends you see here. Like between these two things, it is far more persuasive to join them with a smooth curve than to believe that there is a big dip here, isn't it? This is the runge phenomenon that we talked about yesterday. So I just thought I'll illustrate it with a data example. Okay. So there is perils in making a model overtly complex, and there are perils in making a model overtly simple. Right? And there is, however, a partial good news. There are mathematical techniques to overcome this. It is called regularization techniques. The given regularizers bring more data. Of course, lots of data regularizes your math, your models. But in the absence of that, if you can't do that, there's a whole set of techniques that we won't go into because that's a part of a full machine learning course, that actually you can have your cake and eat it too. You can start with a fairly complex model and tame it down, right? You can tame down the oscillations, dampen the oscillations. So when you dampen the oscillations, that process is called regularization. You get a model that is like this. It's a little bit more persuasive. Nevertheless, you see this little bend. It has improved, isn't it? Look at this. This was a pronounced mistake. Where my mouse is? Do you see that, guys? Are you persuaded? This is very, very unconvincing. Now it has gotten significantly reduced. And the model is a little bit closer to a sine wave, right? Isn't it? So this sort of technique is called regularization, right? It's dampening it down to simplicity. So you take a complex model and then you put pressure to simplify itself. Right? And throughout machine learning, you see these techniques to start with a complex model and then to induce pressure on it to simplify itself. Those are regularization techniques. So now I'll talk about classifiers. Let's come to classifier and take a simple classifier data. Did we start with the blueberries and strawberries? Not very convincing data on blueberries and strawberries, but we'll pretend it is. Right? So can you in your mind imagine a decision boundary going through it? One can imagine a diagonal decision boundary, isn't it? Also, looking at the data, you can rest assured that no model in the world will perfectly classify, because there is inherent overlap in the classes. The classes are not well separated, isn't it? Therefore, and this is some beautiful plots and etc. etc. I'll leave that to you. So we won't go into it. We come up with a classification report that says accuracy is 93%. That is quite believable, isn't it? If you look at this data, achieving 93%, you have a tiny band of confusion in between. 93% accuracy is quite believable. And there are other metrics, like this is what I was talking about, area under the ROC curve. And we have precision and recall and so forth. And this is a plot of the decision boundary. Can you see? Right? The white band is where you're not sure. And I've just visualized it with the data a little bit more pronounced. And that's that. If you want to see a hard line for the decision boundary, this is your decision boundary. This, by the way, the equation that we wrote, that logistic equation that we wrote, is literally the log odds is equation of a line. And this is it. That equation of the line is represented as log odds. So there are other techniques that you can use. We won't go into. Then I'll go into another data set. Oh, what about this? There are 4 blobs of data. There is some small degree of overlap. Now, this is what is called multi-class classification. There are 4 classes, isn't it? If you want to think in terms of fruits, there are 4 kinds of fruits. And now you have to identify which is which. You use techniques, so this is part, again, data visualization of the data. Data visualization is of high value But in any case, you build a model, and it's a logistic regression model. You can build it. Let's look at the confusion matrix. The matrix here is looking a bit small. Maybe I can make the fonts a little bit bigger. Look at the diagonal. The diagonals are still pretty impressive, but they are errors, expected errors. Here's the confusion matrix. The diagonals are doing pretty well. And there are small errors, 4 errors here, 2 errors there, 10 errors here, etc. there. This model has a pretty high sort of, I didn't print out the accuracy numbers, but yeah, it is a, did I print out the accuracy? Yes, it has a 97% accuracy. Pretty good, isn't it? For a model like this. It does that. Then you could have done it with alternative models. There are many, many models, many, many classifiers available that you could have thrown at the problem. I'll take another problem. We sort of talked about this problem, isn't it, a little while ago. So we take this problem, and again, you can imagine with your eyes what the decision boundary is. So guys, here's the thing. In 2 dimensions, you can visualize. In higher dimensions, it's hard. Because if all of the world was 2-dimensional data, perhaps classifiers wouldn't be needed. Human eye would do the job, right? Immediately draw the decision. But because data presents in high dimensions, we don't have that luxury. Once again, if you try to model it with just a line, with the logistic regression, which is a modeling of a line, it's overtly simple. It won't do well. Like, for example, this classification along this diagonal line is totally not correct. So what about a better model, a more complex model? And then you bring in models like this also. Now you bring in a different kind of model. These are called quadratic discriminant analysis. I won't go into it. Or you can do it with same thing, linear logistic regression, but the linear part will contain polynomial terms. Right? It will have polynomial terms. When you add polynomial terms, then
quick question: can you have? I mean, does the decision boundary have to be a continuous line?
No, it can be. So, for example,
can it be like, for example, 2 concentric circles?
Of course, it could be. So, for example, a donut. Right. So whether a point is on the donut or in empty space.
Yeah.
Right. So there are 2 decision boundaries actually.
Yeah.
For the
exactly.
class. Right?
Yeah.
So that is it. Or islands in the sea.
Correct.
Where is land? Where is sea? Where is water?
Yeah.
Lots and lots of decision boundaries are there.
Okay. So you can have as many decision boundaries
as possible.
But then there's a risk of overfitting.
No. Decision boundaries, if they really exist, you better find them. Like, for example, if you're a ship and you're going through an archipelago, you better know where the islands are, otherwise you'll crash.
Yeah.
Right? So this is it, a good model. So isn't this a much better model? It does such a good job of identifying the 2 classes. Right? And so there are classifier models that will help you do that. Now you might say, last time and this time, I seem to be bringing toy models. What about real life? So I would like to end today with 2 real life examples, one for regression and one for classification. For classifications first, let's take the example of the breast cancer data, Wisconsin breast cancer data set. It's a classic data set. It has, so what happened is that it has a long history. It was done in the 90s. Scientists, so there is a little bit of a history to this, as always, to famous data sets. Obviously, breast cancer is pretty scary. But if there is a suspicion, you go with a big biopsy, like you go and scoop out a lot of tissues and put it under the microscope and see, oops, is it that? And that leaves a scar, and it's painful to do that. And most of the time, you come to the conclusion that, no, you're healthy, you're just fine. Right? So it leaves a scar. So people were looking for ways to not be so invasive. One of the ideas that came out was, and that technique is still around, it's called fine needle aspiration. Actually, it's very, very popular in the global south. What you do is you go in with a tiny needle and aspirate out a little bit of the tissue, tiniest amount. And then what you do is you put the tissue under the microscope and look at it histologically. So these scientists, what they did is they said, what if we measured properties of the tissue, like its diameter, the texture, the perimeter, the area, the smoothness, so on, and they went overboard. They just measured all sorts of properties of the tissue, cells, right, of the cells in the tissue. Why would they do that? Because, well, cancer cells are fast replicating, right? And so they tend to be tinier cells, right? They never reach full maturity and they divide quickly. So there is a method. These are good features to do. And so they got all of these features out, and then they asked, can we use a machine learning to do the diagnosis after that? Right? And this is one of the earlier efforts to apply machine learning or AI to medical domain. They did have partial success, and we'll see. So from this data, they found that fortunately, benign tumors are far more than malignant tumors. In other words, when there is a tumor, most of the time, it is more likely that you have something benign and not so harmful or harmless than the fact that you have a malignant tumor or cancer. That's a good observation. This is a bit of statistical analysis, etc. I'll skip it for now. When you build a model using exactly what we learned today, and a lot of data visualizations here, but so the first thing you want to do is, how would you know that your instrument is any good? You need to do this. You need to create a dummy classifier, baseline. Remember the doctor we talked about who tells everybody, my dear fellow, you'll be fine. You need to create the equivalent of that. So the equivalent of that would be a model that tells every data point it's not tumor, right? Because benign data points dominate over malignant data points. So you take a classifier which has a simple rule. It will always say no to tumor. How accurate would that be? So it turns out that is 63% accurate, because 63% of the time it's a benign tumor, right? So that makes sense. So you would agree that it is a worthwhile exercise when doing classifiers to always first baseline with a dummy classifier. It is actually, when I look at people's projects, etc., it is one of the first things I find missing, broadly missing. People are in a hurry to build a fancy model. And if I ask them, so how do you know that this model is better than no model at all? Right? So then they don't know. So this is the way to know. You build a dummy, you always start with a dummy classifier, right? And then you move on to something that is a little bit better. So now you look at a logistic regression classifier, you just take one variable, right? And you realize that you take one important variable, you just pick which is the best variable to take. And I happen to know that, so I just took only one variable. So now it leads to the fact that it is 90% accurate now. So that is the lift, isn't it? From 63 to 90 is quite a jump. 63 is like, what is it? A 37% error rate. And now you have reduced the error rate to 10%. It's almost a four-fold reduction in errors. Doing pretty good. Single variate model. And then you bring in all the variables. And then you notice that your accuracy goes to 97%. Well, that's something. And as I said, 97% is impressive. It's at the borderline of becoming a meaningful diagnostic tool at the time. By the way, I will end with a little bit of interesting history. This was in the 90s, and people were building pretty complicated models for classifiers and regressors. They were building decision trees, random forest, and many, many things in those days, and support vector machines and so forth. And they would bring in all these variables, and computers were getting faster and making these complicated models possible. Right? At one time, just building a big decision tree used to be hard computationally. So all of these things were becoming possible, and there was quite a fervor for complicated models. And then came a paper, I believe the professor's name was Professor Holte, from New Zealand, the other end of the earth. And he said that actually in most data situations, you don't need to complicate it. Just pick the best variable, one variable. He called it the one variable rule, right? Pick only one variable in the data, and usually that will have overwhelming influence. And you will see that with that variable, you get very close to what the best algorithm will give you, right? And you can see that validated. The best, I mean, using this, well, I wouldn't call it the best, but logistic regression with all the variables thrown in is giving you 97%, and with just one variable is already giving you 90%. Right? So this is actually one of the lessons in machine learning. Before you try something complicated, try something simple. Right? I would say that it has a little sort of an echo of the Occam's razor. Make your model, right, only as complicated as necessary. What is the simplest model that can capture your data, or be useful? And sometimes just one variable model can be quite useful. Not in this situation. In medical situation, a 10% error rate would be a disaster, right? But perhaps there are many other situations in which a simple model suffices. So it's worth considering. So I'll end with that, guys. We did classifiers. Let us review what are classifiers. They help you build decision boundaries, separation of classes. They help you predict, is it this or that or the other? Is it a cow, duck, or horse? Is it a blueberry or strawberry? Does the person have cancer or not? And so on and so forth. Okay. We talked about accuracy as a measure. We had a warning that accuracy needs to be contextualized with the class imbalance. As you saw here, 60% accuracy is from the 63% accuracy is from the dummy classifier. Not at all impressive, right? So you need to do much better than that. And look at the other metrics, precision, recall. I've left it as a small homework for you. And all of these things are with, today we have gone on a little bit long. This is, the library is scikit-learn. It's very easy to learn, guys. Scikit-learn is a simple Python library. And a lot of machine learning has been reduced, this sort of things too. You notice there are just 1 or 2 lines of code quite often. I'll give you an example. This correlation. To find the correlation between variables that we learned is just a couple of lines. Then, yeah, this is it. To build a model is just 3-4 lines. From here to here, I've taken the data, split it up, and actually built a whole model and gotten the predictions out of it. So scikit-learn actually makes building traditional machine learning model very easy. Likewise, PyTorch for neural networks makes it very, very easy to build neural networks to solve problems. So, so with that, I'll stop. If there are any questions, please do ask. All right, guys. So if there isn't anything, I will then close today's session. Thank you very much for being part of our learning journey. I hope it is as much fun for you guys, or almost as much fun for you guys as it is for me to do all this, to share all this. It's fun, actually. It's a beautiful, beautiful subject.